of Atlantic sturgeon within the Mid-Atlantic Bight over 12 years. So just as a brief outline, I'm going to introduce the data set that I've been working with, and really this presentation is just to give an overview of this very large data set that I've just started working with and really digging into. I'll go into a little bit of the methods. There's one thing I really want to mention that was a little bit of a wrench in kind of what I thought I was going to do. And then some results. I specifically looked at some residency events and rate of movement, and then future directions. And then we have our nice Atlantic sturgeon picture there for anyone who isn't familiar exactly with what they look like. But so to start off, the last talk was about active acoustics, but my lab was with passive acoustic telemetry technology. So this is a map of our acoustic arrays that are incorporated into this data set. Throughout the 12 years, we've had about 4 million detections of Atlantic sturgeon from 718 individuals. And then I just wanted to point out that the 158 receivers in the 12 arrays over the 12 years have not been out for the same periods of time. These are also similar arrays to what Kim McCown was talking about in her plenary talk if you were there this morning. But this is a combined data set from several different projects to make up this 12-year data set. But you can see we've had a few out for longer periods of time, namely Rockaway, Jones, Fire Island, and Montauk. So just a little bit about passive acoustic telemetry. Our Atlantic sturgeon are surgically implanted with V16 tags, which are pointed out with the red arrow. These tags have a 10-year lifespan, so once a fish is tagged, we can detect it for up to 10 years. And then the receivers pictured right next to it, right here, oh, can't see that. But the receiver pictured next to it, the models have changed over the 12-year data set. The most notable changes include incorporation of temperature sensors, which allow us to collect environmental data at the same time as the acoustic pings. And then they're also equipped with acoustic release now, and that's an acoustic release receiver pictured there. But acoustic releases allow us a little bit more ease in working with them because we don't have to dial on every single one to recover them. And it also makes working offshore simpler. So something about the receivers is that they have a detection radius of up to 1 kilometer, meaning a tagged fish can be detected anywhere within the 1 kilometer radius of the receiver. And this is highly dependent on conditions as well, so this radius can shrink if conditions worse. And this causes a little bit of my wrench for my rate of movement calculations. So enter another array that wasn't mentioned previously. It's not included in this data set. But it's our Orsted Wing Farm array that we've just put in. And this array has a special feature in it that we call the VPS array or a fine scale array. And so these receivers are put close enough together that a fish that swims in there is detected by 2 or 3 receivers at a time. And this allows for triangulation of the fish's exact position within the array. And there will be more talk on the Orsted array in 2 talks from Cora. But so my sturgeon speed limit, I used the data from the Orsted VPS array to calculate how fast our sturgeon were swimming through this area. And this was nice because we just got our data processed for a full year of that array being out. And I was able to do this with 155 sturgeon individuals. So the image on the left is from August 2021 to April 2022. And each of those individually colored lines is a sturgeon individual swimming through, and then each point on the line is every time the sturgeon is able to be triangulated. So I calculated rate of movement between each point for each individual, and then used all that to make my speed limit. So on to some results. This is kind of a very big overview picture of the detections that we've gotten in this array, or these in this data set throughout the whole time period. I want to draw attention to, I ordered the y-axis for our receivers from the bottom of the y-axis is closer to the Hudson River, whereas the top of the y-axis is further away. And so, especially in Montauk that's been out for nearly the whole time, we get these nice little packets of detection when our sturgeon are moving through because they don't tend to hang out by Montauk. Versus in Rockaway, which has also been out for a very long time, we get the bigger circles. The sturgeon are hanging out there much longer, indicating that they hang out and aggregate in the Rockaways before and after moving upstream. So for residency, Residency is defined as when a transmitter is detected more than 2 times at a receiver, and then a residency event ends when it's detected at another receiver or it times out after 12 hours. And so the sizes of the circles indicate a longer mean residency duration and then also the position on the y-axis. And these colors are also reflective of the different arrays. But pretty much what I want you to get from this is that over all years, the arrays nearer to the Hudson River have longer mean residency duration. And this once again supports that sturgeon are aggregating in the rockaways before and or after migrating into the rivers. For my rate of movement, my speed limit, the max speed I found was 1.31 meters per second with an average around a half a meter per second. So I used this number to cut off any erroneous measures of our sturgeons swimming very quickly from one receiver to the next, perhaps in times of very good conditions when they were able to be detected in that 1 kilometer line between receivers. And I wanted to say that this number is consistent with other estimations of sturgeon swimming speed over longer distances, which is also really nice. And then for rate of movement, I broke it up by season, and I put the months of the season on the figure. I used seasons from a paper in 2017 by Melanchuk et al. That looked at sturgeon movement off of the south shore of Long Island. And I did this because I found that the different ways you define the bins, so if you split them evenly 3 months per season, has a big effect on kind of what the data looks like, and that's largely because sturgeon migrations are driven by temperature, not by our arbitrary decisions of when seasons are. So I decided this was the best way because it's kind of impossible to be like, oh, when it's above X number of degrees for over 12 years. But this is nice. It's agreeing with the things that we think we know about sturgeon, which is nice to see, and I'm excited to keep looking into the sturgeon data set. So for future directions, I want to investigate how the trends in residency and or rate of movement change over the length of the data set. I'd like to calculate centers of activity over time, and then I want to expand to more species as their respective data sets grow. This sturgeon data set is amazing, and it's 12 years, and there's hundreds of individuals tagged. And it's nice to see what we can do with other fish species, especially as we get more and more tags out. And then I have a lot of acknowledgements because this is a 12-year data set. So it kind of started with Kim McCowan, Lindy Heist, who spoke this morning, and then Mark Wiggins and Josh, Keith Dutton, and Evan, who worked for our lab, and then also the New York DEC, who's continued to fund our acoustic receiver projects over this whole time period. Any questions?